Hello? Test 1, 2, 1. Okay, it's day 2, 14 o'clock, and now we have a talk about Batman, the not quite well-known, but soon to be well-known protocol for especially the Freifunk community. And the talk will be about how to bring the routing from layer 2 down to layer 2. I'm sorry, I mixed it up. Up from layer 3 down to layer 2, and well, give a welcome to Mark Lindner from Berlin and Simon Wunderlich from Chemnitz.
Thank you and welcome to our talk. I will first give a short outline. We will introduce to you, maybe you don't know what the routing protocol is, so we will explain and what is different in Batman. But we won't talk about Batman here, we will talk about how to go down the layers from layer 3 to layer 2, and we will talk about the problems which got solved automatically and the new problems, and we will show you how we brought this into kernel space.
Well, first of all, we should... Can you hear me? I'm not sure. Yes? Okay. First of all, some background about what we are talking about. Usually, we have the idea to build a wireless network somewhere in a city or in a rural area, and you have a couple of devices you can see, and the green ranges show the range of each device, and the green little bubbles show the interaction between the devices, so data is passing from one device to another. But the usual geek who wants to create such a network faces two major problems we want to outline here. First is the Wi-Fi layer. The Wi-Fi layer is a bit tricky. You cannot see it, you cannot touch it, it is there, and it is interacting with a lot of other devices and a lot of other interferences. And so we have an example scenario which could be 6 o'clock in the morning. You have some WRTs which form the backbone of your wireless network. These are the blue little machines. You have some notebooks connected to these WRTs, and then you have some cell phones with Bluetooth, and they disturb the signal, or you have some microwaves, they also disturb the signal, or you have foreign networks which disturb the signal. So what is the problem here? The problem is you cannot configure it. There is no config file for the Wi-Fi layer. It's just there, it's invisible, and the geek has to leave the notebook aside and has to climb onto roofs and build antennas, and that's usually a big problem. But so the geeks come to us and say, oh, we have a nice protocol. Would be very nice if your protocol could solve the problem and I can stay in front of my computer. And our protocol has to solve these issues. And if we go to the next slide, we see that in the evening the network looks much different, because some devices were switched off and other devices were switched on. And again, our protocol has to manage all this. And now comes the second major problem for geeks, which is, you can go to the next slide, is the geek itself, because the geek itself will create a complex network. We have VPN connections, we have ad hoc networks, we have infrastructure networks, all connected and all should talk, and it's an endless way of configuring and bringing all these nodes together. And you can see down there is maybe a LAN, and up there where the Ethernet is shown, we have maybe a big church, and then you have some internet points, gateways which offer internet connection. And during the time I'm involved in the Freifunk network, I thought after the first year, oh, now I know all the setups, and all the time new people coming up and say, oh, I have a new idea and make it more complicated. And so it's endless, the configurations I've seen. And all that should be handled by a routing protocol. Well, you can do all this manually. You can just configure your routing tables. But you will find out that this is quite a task to do, because it's changing all the time and everybody has ideas how to improve it, how to make it better. So you want a way to do this automatically. And here is what the routing protocols do. You have some kind of software, and you start it on all the nodes, and then they talk to one another and find the best ways to route your traffic. This is just the basic idea. I know that some people here are quite familiar with routing protocols and others are not. So we don't go too much into detail. We just imagine that we have some kind of software which should manage all this stuff, so all this complex configuration and the Wi-Fi layer. And there are common approaches, link state routing or other source routing, but we came up with another solution because, well, as a usual geek, we said we can do it better. So we have a new approach we call it Batman. And of course, we have an interesting name for it. It's an abbreviation, Batman, Better Approach to Mobile Network Networks. Of course, we are the best. What is the difference? The main difference between other approaches is that we don't calculate all the ways between all the nodes, or we don't, we just say, we are here, every node says, hello, I'm here, and all the other nodes see, oh, there's a node somewhere, and everybody keeps in mind, where is my best neighbor towards this direction? That's basically the idea of Batman. I know there are some people in here who like to discuss all the fancy routing stuff. I suggest that you join us later and we can have all the big discussions about link state routing or this routing or other routing, but we want to talk about kernel stuff, we want to talk about layer stuff, so we don't go into much detail here. Just keep in mind, we designed this protocol for wireless networks. It means our protocol wants to have a lossy network. Our protocol needs packet loss. Otherwise, it won't work so good. And the major advantage of our protocol is that we do not have a single node which knows the whole topology of the network. In fact, we spread the information about the whole network over the whole network. Every node knows a bit about the network. So it's a bit about what we heard about Erlang here. We spread the information to reduce the cost on every node. But as I said, we just assume there's some magic doing all this fancy stuff, and we think it works. Or you can find out by yourself. But we go now into another part of the routing stuff, and yeah.
Okay. First, we look how does a routing protocol daemon works now. This is for Batman, but I think every classical routing daemon works like this. We have the brown part is what this daemon manages, and the blue part is what the kernel manages. So you see, the daemon only exchanges routing information, for example, on some UDP port, and sets the routing tables. So payload traffic is routed by the kernel. So if a packet comes in, the kernel looks onto it and sees the routing tables, and I have to forward it on this device to this neighbor. So we don't have to manage this. We only set routing tables. And of course, these are IP routing tables, so it only works with IPs. We could also use this for IP version 6 or something else, but things like DHCP or other protocols don't work. And administrators have to make sure that everyone has a unique IP. So, or you have IP collisions, and this will, of course, not work. And if you have fancy network setups, like we have seen before, you have your local network and maybe an access point in your home, and you want it all to be routed through the whole city, you have to make some effort and have to announce this, set your routes manually. And this is one thing which can be solved with our approach.
Let me add one important point here, which is basically we have a chicken and egg problem in a mesh network, because you want to join the network. For joining the network, you need an IP. But how do you get the IP? Usually there is some kind of central server who has the knowledge about all the used IP and used IPs and the unused IPs. So you need internet access. So you need to join the network. So you're back again in the first step. This is a major problem we face, because we have a lot of people who really don't have internet access, and they only can get internet access if they join the network. So the basic problem here is that we need this central instance which can give you an IP or some kind of configuration before you can join the network. And this is one of the major problems, because next to the problem I just mentioned, every city, for example in Germany and the German Freifunk networks, makes it different. I mean, in Germany, in Berlin, we have a big web server where you can click your IP. In other parts of Germany, everybody makes it different. So if you move from one city to another city and you want to join the mesh network, again, you have to find out how they handle the IP business, and then you have to configure your IP, and then you can join the network. And that is a major problem in this approach here.
There was a question, no?
Oh yeah, if you have a question. Yeah. Wait a second.
Wouldn't IP version 6 auto-configure solve this problem with IP addresses? Would it? Could it?
This is a longer discussion.
Okay, sorry.
Yes and no. It is more complicated. I don't want to go into the deep steps of IP version 6. There are some ideas, but it is not perfect. I mean, that depends. Let's talk about this later, okay? If we have enough question time, then let's discuss the IP version 6 issue. Okay? There's another question.
There is some approach in IPv version 4 that is auto IP, that it asks for ARP about if somebody has his proposed IP and then he gets this IP. You know what I'm asking? Auto IP.
If we have auto IP configuration.
Yeah, to get some IP. It's a private IP, but should work maybe.
I did not understand. Can you speak a bit louder? That's the main problem here.
There are approach that it's auto IP, that
Yeah?
it's for getting an IP in a network.
Automatically, you mean?
Yes. This doesn't solve even.
Well, what approach do you mean? I know that some people at olsr.org work on auto configuration IP issues, but all the approaches I've seen up to now are not perfect. They still have glitches. They still have, problems left and the right side. And usually in a practical network, you have these glitches more often than the usual case, or you have more trouble with them. So I've not seen any auto IP configuration which works very good. But I don't know everything. So if you have a good solution, maybe we talk later. The main problem is that the routing daemon itself needs an IP, because the routing daemon will send out a packet and writes in the packet, this is my IP address. I am here. So the problem is, how do I write I am here if you don't have an IP address? So all this, there are some approaches of I choose an arbitrary IP address and use that one, or some kind of unique identifier or something like that, they have a lot of problems. But yeah, so it's not. Okay. More questions? No? Okay, then we can
Okay,
continue.
then we go on. Okay, we wanted to try layer 2, and this we first have written a user space proof of concept daemon, which does the task we wanted to do, but it has some performance problems we will show you later, and so we took the next step to the kernel space. And instead of IPs, on layer 2, you have MAC addresses. And MAC addresses can be used as identifiers. They should be unique per design. Maybe you have already seen 2 devices which have the same MAC addresses. This sometimes happens for manufacturing failures, but usually it's unique. So you just skip the auto IP problem. We provide a virtual switch port, a tab interface that is, and you can imagine the layer 2 Batman as a big distributed switch. And every node has one switch port. And you can connect other switches or bridges at this port, just as you would do at your switch at home. Yeah, so you have a virtual interface and you can set IPs or IP version 6 addresses or anything else, and it will just work, and all other neighbors are just one virtual hop away. So we have nothing to do for this to work because we are on layer 2. And you can use this approach even to bridge multiple interfaces like a Wi-Fi connection and an Ethernet connection. We have seen the example with the church where you have an Ethernet backbone and Wi-Fi to the rest of the city, and you can just use it as a bridge. Here's an example how you would use this. You have your interface and you can set an address, set a gateway to your next neighbor which would provide internet, or you can even get an IP address with DHCP. Yes, and this in contrast to the other slide, we have to manage also the payload traffic. All the payload traffic is encapsulated in Ethernet frames, and we have to handle it all by ourselves. We do not care about IP addresses. It's just as a switch does not care about IP addresses, it just transports it. And yeah, we look into the Ethernet frame, decide which other node should receive it, and then we route it just like the layer 3 daemon routes it through the network. This is, shows the implementation, the data paths. So if you send a packet, it will come into the tab interface, BAT0, and we look it up in the MAC translation table. The MAC translation table is also which every switch has, and we decide which node should receive the packet. And after we know which node should receive it, we choose the best neighbor which can forward this packet for us. And after we have this, we just pass it to our neighbor and he does the same. Also chooses the best neighbor and forwards it until it reaches the final destination.
Do you encapsulate it, or do you just send it through as a raw packet?
Yeah. The question was here. The question was here.
Or do you just send it out?
Yeah. Yeah. So the question was, do we encapsulate the packet or do we just send it out? Maybe this was a bit. Kannst du mal ein bisschen zurückgehen? This was a bit quick. Look at this slide. actually we created our own Ether type. Yeah, it is just, we just hijacked the number. Yeah, you can see the number. It's 0842. Seems to be an obvious number. He showed, some slides before, he showed that Batman on layer 3 just sends UDP packets and manipulates the routing table. And here we do something different. We send Ethernet frames to get our routing information, and we have this interface he showed, the BAT0 interface, and you set your default route on this interface, and this directly ends up in the routing daemon, and the routing daemon will take your payload, your traffic, and encapsulate again this traffic to transport all the data over the network.
So we take just the Ethernet frame as it is, encapsulate it in our own Ethernet frame, and send it out, and it will just come out on the other end as we put it in.
Okay. This is a very crucial part here. Are there more questions? Maybe we should... No? Okay. Falling asleep, half of you?
Okay.
One more question?
Do you handle any form of retransmit? Or do you leave that to the higher layers? So if you encapsulate your packet and send it out across the mesh and it disappears, do you attempt to retransmit it, or do you just let normal TCP handle that?
No, it will just be dropped, because on usual Ethernet it will also be dropped. You might know Wi-Fi tries to retransmit it on its own, but we would just drop it. We don't try to retransmit it on our own.
Yeah, the upper layers handle this kind of traffic loss.
You have TCP for this if you want to retransmit something. It will make sure, we hope so. Okay. 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 So I've said we have a big switch, a big distributed switch, and you can also plug in another bridge. You might know the Linux or bridge. You can add your other interfaces, like if you have a Wi-Fi interface and offer an access point, or if you have an Ethernet segment on your computer, you can put them all in one bridge and add them to the Batman mesh. And of course, all other Batman participants have to know that which participants are behind this one node. For example, the cell phone and the laptops, they have all their MAC addresses, and we have to memorize them and build distributed MAC translation tables. And so this works. Our Batman nodes watches the packets and the source MACs and remembers them. And then it will flood these MAC addresses through the network. This is done in HNA messages. This name comes from OLSR, I think, and we also used it in Batman. It means host network announce. So it's just the same name, so maybe you are familiar with it. And it is for announcing that behind this node, these are these MACs of these participants. And with this, we have decentralized MAC translation tables. Everyone knows all the participants behind all nodes.
Let me add a few words here. First of all, you have to imagine that on layer 3, which is our Batman implementation, you have maybe 3 or 4 nodes, and your traffic goes through these 4 nodes, and then you have maybe you request a website or something, and then you have a normal HTTP request, and that goes down to layer 2, it's been transported to the second node, goes up to layer 3 because you have IP addresses, goes through all the firewalling, goes again down to layer 2, is retransmitted, and so on. And with this layer 2, the packet goes only once down to layer 2, and is then retransmitted always on layer 2 without being brought up to layer 3 or higher layers again. So for every node, it appears like one hop. It does not matter how many hops, how big your mesh is. It's only one hop for the higher layers. It's real like a big switch. You can connect all kind of devices and hide them in this big switch. And here comes the interesting part. You can even, in this bridge here shown, there can be another access point where you have these laptops running in infrastructure mode, and you build a bridge around it, and then these laptops can easily connect to the network. If you have a layer 3 implementation, you have to assign them IPs, you have to tell the rest of the network about the IPs, you have to set up routing, forth and back, and there are several solutions, and all of them not quite easy to use. And here, you just connect your notebook. The Batman on this side will see, oh, I have a new notebook, I announce the MAC address, and then it can take part in the network. As easy as that.
On layer 3, you usually have to say, oh, I have this subnetwork, and I have to announce this subnetwork and its subnet mask, and the others have to notice this and have to add this in their routing tables. And this is just, you plug it in and it works. And another interesting side effect is you have the decentralized MAC translation table. So every node has the MAC translation table, and you can use this for visualization. So I used this for debugging in a real setup with 8 access points, and I set them up. The numbers on the edges is the quality between those nodes. 1 is the best, and all above is worse. And the green or blue one is my laptop, and you can see it's announced from access point number 4. This means I'm associated with access point number 4. And so I was going through the hall where I set this up, and I could see, oh, I'm behind access point number 1, 2, 3 now, and those are connected. Yes, this is a nice side effect, and you can see all the clients behind all the access points. Okay, this is great. This proof of concept implementation works quite well in the user space, but the problem is performance. We want to run this on minimal embedded systems, small access points like the OpenWRT or cell phones. And you have seen we have to manage all the payload traffic. It does not the kernel does it for us. We have to make it ourselves. So the typical path is we wait for a packet, select it. When we have found one, then we read it, copy it in the user space. We find the next hop and update tables. This is our hash tables, lookups. This is very fast, and then we write it out to some of the interface. And all those system calls, read, write, and select, take quite some time. You have to switch from kernel mode and back, copy the packets, copy them back into the kernel space, and this is overhead which we don't really need. And it works for low bandwidth usage, but if you really want all the throughput what your network interface card can do, you won't be happy with this. So the next step is to kill this performance problems, and we go into the kernel space. So we don't have the copy back and so forth.
Yeah, so as already mentioned, if we reside in the kernel space, we can avoid a lot of copying. Actually, it's really amazing what you can do in kernel space. We get just one buffer, a packet's coming in, and we don't have to reallocate a buffer or copy or write it somewhere. We just look at it, oh, we have to send it there, and then we send it in the send queue, and then the buffer is sent out. There's no forth and back between user space and kernel space. So this is where we wanted to go. And another amazing part about the kernel is that if you write a user space application, you usually have one process or one thread. And if you want to make it pretty fast, then you have to work on the things the thread can do in the same time, because you wait for a packet there and you want to send it there, then you again wait, and you have a lot of synchronizing, and this is a lot of work the kernel does on its own for us. In the kernel space, you just hang on your functions in specific sockets and stuff like this, and then they work on their own. You just have to pay attention on shared data, and the rest is so asynchronous that we want to have it. So actually we moved the whole layer 2 implementation into a kernel module, which you can download right now, and you can compile it and load it. And I think a lot of you are familiar with user space daemons, but the kernel space is a bit different, so I will briefly outline the main differences. First of all, there is a new way to configure the routing daemon. We just set up a new directory in the proc file system, where you have the usual files, or well, the usual names we always have. You have gateways files, you have interface, logging, and some other fancy stuff where you can tweak a bit the kernel module. The main difference between a daemon and the module is that the module always resides in the kernel space, and if you want to tell the module now, please start, then you just echo an interface into the interface file, and then the daemon will start to work on that interface, not the daemon, excuse me, the module, of course. You can run the module on several interfaces. You just echo more interfaces into the file, and then the daemon, I'm still in daemon mode. Okay, we are back. We are now in kernel mode. The kernel module will work on the other interfaces as well, and you can deactivate it by just writing nothing into the file. Yeah, can go on. So the logging is a bit special, because in our user space implementation we had a nice Unix socket where you could connect to the various log levels. It's not so easy in the kernel space, but we provided a log level file where you can change the logging. It's similar to what you know about Linux file system access rights management. You can see we have critical, we have warnings, we have notices, and you can activate them by echoing the number or by echoing the names of the logging levels. And you can just read it from the log file, and it's endless read, and the kernel module will add the logging stuff. You see the module was loaded, and then later we changed the log level, and you will find routing information or whatever information you could have been interested in. So what can we say about kernel development? Oh, a question. Yeah, okay, questions down there. Raise your hands again, please.
Why didn't you use a syslog instead of a log file in proc?
Sorry, I did not understand. What did you understand? No.
The log file is stored in the proc file system.
Yes?
But there is a syslog facility in Linux for this kind of stuff, usually.
You mean why didn't we use this file system?
The syslog file.
Syslog.
Yeah.
Okay, excuse me. Actually, we run on embedded devices, and there's not a whole syslog facility around it. It depends on the device, and there's a lot of stuff which is stripped off, and we did not want to spam the dmask output, because if you switch on, for example, the Batman routing level or the other levels, you have a lot of information, and you can fill up hard disks with it in quite a short of time, and that is why we separated it. If you have the critical warnings, or the critical information, they are always logged to this log as well. But the other log levels, they are specifically only for Batman, for the two reasons I just mentioned. Don't there have more questions?
Yeah.
You just mentioned the log in proc. How big is the buffer for storing these log files?
How big is what?
I mean, you have to store somehow a buffer somewhere with the latest log, and how big is the buffer? Can you
The
configure?
buffer is about 8,000 bytes, or 8,192, if you want to know exactly. Yeah, here's the question.
Haben noch mehr Fragen?
Yeah, so there's basically questions and comments. One comment is, I mean, this dedicated logging system, if you ever intend to merge something like that in the mainline kernel, you know that this is not going to be perceived pretty well. So
I know that. Yeah.
Okay, you're aware of that. The other thing is basically, I would be interested in more details about that implementation and whether it's entirely inside kernel space or whether you still have some kind of control part in user space.
No, it's entirely in the kernel space.
Okay, no, I forgot the other question, sorry. Entirely in kernel space. So do you think it makes sense to have this entirely in kernel space? Because usually what people tend to do is to differentiate between the control plane and the data plane. So you have the actual packet forwarding and your neighbor information and that kind of stuff in the kernel, but the control processing, as in the protocol you speak between your nodes in some user space process, which then just updates the neighbor tables and that kind of stuff inside kernel. That's sort of a structure that people would typically choose in the Linux kernel.
Yeah, we did not, maybe we should discuss this later because we did not finish yet. There are more reasons why we do this, and but I can tell a bit about it because you asked. Actually, what we've done now is we just ported the user space daemon into kernel space. We want to do more. Actually, the idea is how can we save even more bandwidth? How can we make it more efficient? And there are several ideas floating around. For example, embedding the hello messages. We broadcast the hello messages directly into the Wi-Fi layer or something, which is broadcasted anyways. Something like that. And that will be more difficult to handle from the user space and all this forth and back. And there's another point. We always keep in mind, we focus on our users. We have a lot of users in Freifunk, for example. They are not really experts in routing, not experts in kernel development and stuff like this. They just want a tool, plug it on, and it should work. And if we have 3 tools and 5 configuration files, and this is the harder it is, the more you will scare them away. And if you just have a module and say, load it, and then echo your interface into the file, and then it works, that is what we want. And we don't have the intention, or not at the moment, to go into the mainline kernel, and so that is not an issue for us.
So. Then I understand this because it's also this architecture, like being a Linux kernel networking hacker, this architecture with echoing interfaces and proc files and so on. Yeah. It's you're going to see lots of tension if you ever intend to do something like that. One final last comment or question is regarding the functional principle, because you basically create one large broadcast domain.
One large what?
Broadcast domain. I mean, what I understood is basically you link together your entire mesh network and it appears as one link layer, as one virtual link layer that's sitting next to your interface.
Yes.
Now, I see severe scalability problems with that, given the amount of broadcasting and multicasting that's going on by, zero configuration, Avahi, MDNS, the entire Windows world and all that one. The number of machines that you get in such a virtual broadcast domain, I'd expect to be fairly limited. Do you have any comments or?
Yeah, that's right. I think if you plug thousands of Windows machines into this, it will just blow up because they're all broadcasting all the time, hello, I'm here, and so on. This, of course, this might not work, but if you have a big Wi-Fi network with maybe 1,000 of nodes and you have very long hops, or you have so much packet loss that it does not make sense anyway. So maybe you can just create smaller meshes and route them again.
But yeah,
Like as you do with Ethernet segments, you just route them again, but you still can plug them together very easily.
Wait a second. You can you can ask your question in a second. Yeah. But this is the question we hear quite often. The scalability issue and the broadcasting issue and all this. Please keep in mind this is a wireless network, and we have a lot of packet loss. And you could imagine, yes, in a perfect network where every packet reaches the next hop, and you have 1,000 nodes, then you have a lot of broadcasting by zero configuration and all that kind of stuff. But in a wireless network, as I showed in the beginning, we have a lot of packet loss, really a lot of packet loss. I think this limits the whole issue right from the beginning. But again, we cannot create a tool which relieves the administrators from thinking. We can create a tool which helps them. But we still need some kind of administration, and yeah, I think this will be an issue in the future, but now it's not an issue. Okay?
Could you use EB tables to filter out some traffic that you don't want, or something like this?
EB tables, you mean?
It's bridge table.
Yeah.
It's similar to IP tables, but for bridges.
Yeah. IP tables won't work, and we did not try it with EB tables yet. We're not sure that works, because as it resides in the kernel space, and we hook into special functions. I've not tested it yet, whether the EB tables functions will be called later or before that. So it may be that you cannot filter with EB tables, but we have to test it. Okay?
Is what you need, can you have two separate mesh networks, or do you need to do some extra coding and add sort of an ESSID so that you can tell them apart?
The mesh networks itself, you mean?
Yeah, could I run two separate mesh networks?
You can have two separate mesh networks simply by choosing another channel or another. I mean, you still have the Wi-Fi layer where you can separate the mesh networks. But why would you do that? I mean, it would be, with this technology, it would be even better. Imagine that all the households would use the same technology and bridge together, and then you could create your own IP network on top of it, or whatever technology you want to use.
But the problem there is it's still all one single broadcast domain. And the thing that the other guy raised about 5 minutes ago is that the broadcast traffic, because it has no TTL, it just
we are
carries on
talking about the
expanding.
future.
Yeah.
So in this future, we could add, special identifiers to only keep the broadcasting in the broadcast domain. But why would you want to separate the networks?
Well, why do we have separate ESSIDs on Wi-Fi networks?
Yeah,
It's
good question.
precisely the same thing.
Yeah, but think it the other way around. If you have, for example, some neighbors between you, and you don't know them or you don't like them or whatever, but you want to talk to the guy behind them, and you could use the same network, because it's not limited by the IP or whatever layer, but you can use them as a bridge. It would be nice, wouldn't it?
So when you do bridging, do you set up your BAT interface, and then if you need to bridge that to an Ethernet interface, do you just use bridge tools and create a BR0 device and add them?
Yeah.
Okay.
Okay. There's another question. Wait for the microphone, please.
I have more of a suggestion for creating different networks on the similar on the same medium. Maybe you could use 102.1q, so you just use VLANs on the lower level interfaces that Batman uses.
Yeah, we already yes. Okay. We already discussed
you
that.
can keep separate networks around.
Yeah. Okay. Here's another question. Here in the first.
Yeah, hello. Can you tell us a bit more about your real life experience? Because 3 years ago we started such a project in Rostock and started with VDS. That's basically the same idea, but not maybe such nice implemented. And after putting the maybe 20th node, everything was crowded with all the things the other question has already mentioned about the broadcast and everything. So yeah, the real life is maybe yeah, very interesting.
WDS, you mean from the specification?
Yeah, from the Wi-Fi
Yes,
protocols.
WDS is a little bit tricky. It just makes bridging possible by using all the flags from the header, and but it is intended only for small networks, as far as I've read. So it builds up a usual bridge.
But basically it's layer 2 already.
It's already layer 2, yes, but it does not do meshing. It does not choose the best neighbor or something.
It's just broadcasting all
It's
directions.
just broadcasting.
Okay, you are right, and choosing the right direction. Yes.
Yes, and this is what Batman already does. This is what the Batman algorithm is about, and we just use this algorithm to choose the best neighbor, and this is what WDS does not do.
Okay, the route selection is a problem. And the other thing I saw it in your table at the beginning, the tool chains for layer 2 are really weak, and I see a problem in the future if you like to support many different systems, not only Linux. What do you think about that?
Well, our real-life experience showed, in the beginning we had the same approach as you mentioned, but our real-life experience showed that by supporting a variety of platforms and systems and so on, you get a lot of problems.
So that's not a basic topic of Batman, to support many different systems.
Well, if you want to port it, you can do it, but with Batman on layer 2, essentially it's not necessary, because if you look at the router hardware out there, most of them run on Linux. You can, well, the WRT or OpenWRT, and they all run on Linux. And you just need one router, and then you can add another router, infrastructure mode, and all your notebooks, whatever system they run on, can connect infrastructure mode, and you do not need to touch all the notebooks. And that is the major problem we faced in the past, because you know, the ordinary Windows user comes well protected with all kind of tools, protecting against viruses, firewalls, and all this kind of stuff, and then we spend hours to first disable everything, because the user itself does not know where to disable all the stuff which is running on its system. And once everything is disabled, you hope that the Wi-Fi card supports ad hoc mode.
But also the users yeah, lost something from their computers. They can't do everything they want. They have to realize what Batman does. So yeah, it has two sides, I think.
I didn't understand the second.
If I have some tools for, maybe it's called EB tables or firewalls, yeah, I can do something I want, and yeah, in this kind I have to bring my own tools again to set up.
Yeah, but
yeah, it's okay. You think about the usual usage of user which is not just want to work.
Yeah, I mean, it came out after some years. It came out the best is to tell the users, buy a router, install the software, and it works. Yeah, even installing the software on the router is a problem. So you don't want more problems. And then we tell the user, there's a firewall which is pre-configured, there's everything you need, everything you want, so just put it there and connect to that router via cable or another access point or whatever. It's much easier and you have less pain.
But if you want to port it, just tell us.
We will help you.
Okay, I think we will go on and okay, a last question because we are late in time.
It will be quick. Did you think about any kind of security or authentication or encryption the data sent through that host that I didn't trust? Any kind implementation in the future?
No, we don't do any encryption. You can use a different encryption from your Wi-Fi hardware. You can use IPsec. You can use open.
Yeah, but
VPN.
the next hop with IM communication, he knows all that case and everything. It's going through his card, and he mentioned he will know what data is in there. So are you planning in the future any kind of authentication in that software?
Well, the question is, what do you want to authenticate against or for? Or I mean, first of all, keep in mind the embedded devices from today are not really powerful machines. So encryption, any kind of encryption, was not done in the hardware, will cost you a lot of CPU power. That's the first problem we have. And the second is we have a mesh network. Means everybody should connect to it and should be able to take part. If you make an encryption on that, you have two choices. Either you share the key with everybody, or you don't share the key and then nobody can connect. So, and you know, in the moment when you find your key on eBay for €5 or something, then you know, you have to change the key again. So we tell the people to use higher layer encryption like SSL or something, as you would do normally if you have, you know, email account or bank account. So, I mean,
it's just as secure as the internet.
I'll catch you later.
Okay, I think we will go on now.
Yeah, I think we go quickly through the rest and then maybe, I don't know, how much time do we have left? 10 minutes.
So,
okay.
Okay, maybe we have some time later and we won't run away. Okay.
A few words about kernel hacking. We are not some experienced kernel hackers or something. We started kernel hacking some months ago, actually in the moment when we decided we want to have that kernel module. So we are the best proof that kernel hacking can be done, and it's quite easily actually, because the kernel itself is like a little universe, and the little universe has all the functions you want, and you just need to find out where are these functions, what are the names of these functions, and how to use them. And you will find a lot of code, a lot of examples in the kernel itself, and it's quite easy to learn and quite easy to write the code. Actually, I was a bit scared before I started, but after I started, I thought, oh, well, that's so easy. Of course, in the beginning, you freeze your system 1, 2, 3 times, and after that, you begin to realize, oh, it may be a good idea to think about your code before you insmod it. But that comes quite quickly. And so I'm really a big fan of kernel programming now. In user space, you have to do such a lot of things, a big loop for getting packets or, you know, writing lists and all kind of stuff. And you find all this in the kernel, you just have to use it. And so I could give you some advice. I mean, clean programming, I just mentioned it, is the best choice you can do. Or you can use printk, it's similar to printf. The interesting point about printk is you can use printk in every situation. You can use printk from interrupts or everywhere, and you just print it and it will appear in your syslog files, and it's quite nice. If everything fails, you get a kernel oops, which is a little stack trace and about all the functions which were just executed. But usually, if the kernel freezes, you already know where it was. I mean, if you ever have written a daemon and you thought, oh, well, yes, there's a problem, but it's unlikely that that will be a problem, so I fix that later. usually some days, months, or well, somebody comes up and says, "Oh, there's a problem in this and this function," and then they say, "Oh yes, I know because there was something I did not fix." And but in the kernel space, you should fix it right away, and then you don't have a problem and don't have a freeze. Another advice I could give is using UML. I mean, I'm not talking about the little language, you know, where you draw fancy arrows and little. No, I'm not talking about. I'm talking about user mod Linux, which is essentially another abstraction layer or virtualization or however you call it. There you can start a complete Linux environment in your Linux, and you can just call it with a debugger in front. It means you call GDB or whatever debugger you like, and call the Linux binary, and then it appears in your debugger. And once your module crashes or whatever, then you can see, oh, it crashes in that line. But I've never used it. I've never needed it. Because when it freezed, I mean, when it froze, then I knew, okay, it was that point where I didn't fix the problem. So don't be afraid, don't panic. I can really encourage you, try it. And we had a little story. We are about 6 people in the Batman project, and 4 to 5 coders, and everybody had his own coding style. And well, of course, that led to some problems. And once we started with the kernel development, we talked about what about using the kernel coding style as our coding style. And as this was a coding style nobody was using, everybody could agree to it. And after that, now we code in the kernel coding style, and it is so readable. And once you get used to it, it seems so clean. And I can really recommend it to try it. Okay, what else do we have? Last. Oh yeah, one problem I almost mentioned is on layer 2, as I said, you only have one hop for all the tools you use or all the programs. If you use ping or traceroute, it can take seconds to the other end and come back the ping, but the ping will show you it's only one hop, because the packet goes never up to layer 3, and so the ping never sees that, oh, there's a next hop. It's like a switch. The same problem applies to traceroute or any other tools which work like that. But it would be nice to see if our little switch works. So we created a BAT tool, the BAT tool chain, which is a set of tools which work on layer 2. Simply by they connect to the user space daemon or to the kernel module and inject special packets. It's a lightweight implementation of ICMP, actually. And the Batman daemon or the module will handle the special packet like an ICMP packet, so that you can see the hops, that you can see actually the real ping, or you can see where your route is going to. I would like to go more in detail, but I think we don't have enough time. Just try it. Yeah, here we have 2 links if you want to try our code or want to hack on it or get in contact. I think the slides will be uploaded somewhere, so you can download it from there. And
I think they are in the Congress Wiki already.
yeah, the Congress Wiki. Okay, so you don't have to type quickly now. You can see it later.
And you can download the code, of course, and try it and compile it, insmod it. Okay, so yeah,
Okay.
that's it. Thank you very much. Thank you. Do we have time for questions?
Short time.
Okay,
There's
short questions.
Short questions and short answers.
Yeah, somebody asked about VDS. Did you read about 800.2.11s standard?
Yes, well, we read about it, but actually it's quite difficult to get documentation because...
There's a proposals online, I think.
No,
I got one.
You have to be an IEEE member to get
Yeah.
documents.
Okay.
I'm not an IEEE member.
But I think the OLPC people
Yeah,
do
well,
know something.
The S standard itself is just a framework for meshing, and they propose two protocols to be used in this framework. One is AODV and the other is RA OLSR, I think.
Yeah, but it's like on layer 2. Of course, it's AODV, I think it's reactive routing, but I think it's layer 2, and I think it's something similar to what you do.
Yes, but ours is only based on the Ethernet layer 2. And the standard you mentioned is
Wi-Fi.
in the Wi-Fi layer 2. And we don't fiddle with Wi-Fi, but we could also do this, and this is one of the ideas we want to try.
The advantage what we are doing now is that we encapsulate it in the Ethernet frame, so it runs over Wi-Fi network, it runs over the Ethernet network, it runs over different networks, and it's not bound to hardware.
Yes.
You can use any hardware you want.
You can easily build tunnels and Ethernet backbones and something like this.
Hello? Okay. What inbuilt protections has Batman against evil nodes who play black hole or something like this? Or poison the routing stuff? Are there any safeguards against this?
Black hole.
Black hole? What kind of black hole?
Yeah, no, like a node just says garbage and tries to poison the network. Are there safeguards against it?
We just wrote a longer paper about exactly that topic.
Or just tries to attract lots of traffic and throw them into the black hole.
Yes, you can do this. Basically, a mesh network relies on information from others. So if the others tell you a lot of shit, well, you have a problem, of course.
Yeah, but you could try to authenticate your node so that no one else could try to impersonate it or something like this.
Then we are back to the authentication issue.
The authentication issue is you can authenticate, but then everyone has to register somewhere. But we want everybody to
Not
to
like
join
Web
it.
of Trust or something?
Huh?
Not like Web of Trust or something?
No.
Okay. Yeah, then
we don't
sorry.
have this.
Well, we can discuss this later, I guess. Then we just.
But the impact is not so big as you might imagine. But we can discuss this later.
Okay.
Okay, thank you for your talk.
Okay.
Thank you.